So we are going to solve this question where we are looking at the a DT graph, a displacement time graph, and figuring out what is happening to the motion. And you'll notice these are all nice straight lines, which means we're dealing with uniform motion. And it's a displacement time. That's important to have in your head. And the first thing it asks is for us to describe the motion of this object. So that's what we're going to try to do. We're going to describe the motion of this object. And you'll notice there's 4 distinct sections. In the first section, it runs from about 0 seconds to 2 seconds. And you can see it's a nice straight line. That means it's a constant velocity and it's moving away because the displacement is getting bigger. So I will say it's moving away at a constant velocity, and that is from 0 to 2 seconds. Then something changes, right? This is still moving away because the displacement is still getting bigger and bigger, but it's doing it at a much faster velocity. You can see it's a much steeper line. That means it must be a faster velocity. So we're going to say it's moving away at a faster constant velocity, and that is from 2 to 3.5 seconds. Now, there should be a transition in here. We haven't talked about acceleration yet. Eventually, we'll make this work a bit better because we do know we can't go from one velocity to another without some kind of speeding up happening, but don't worry about that today. We're going to focus on our uniform motion instead. You'll see then at 3.5 seconds, something happens. All the way along here, my displacement stays at 9. 9 the whole time. Well, the only way that that happens is that the object must have stopped, right? It must be standing still. So it did that from 3.5 seconds to 6 seconds. It just sits there, sits at 9 meters away. And then all of a sudden, the displacement's getting smaller. Well, for the displacement to get smaller, I must be heading back towards the reference. So I'm moving towards the reference. So I'm heading back to the way that I came, also at a constant velocity. That happens from 6 to 9 seconds. So that describes what happened to the object, the motion of the car. The second question asks to find the exact velocity of the car at the 3-second mark. So if I look at the 3-second mark, if I locate it, I am finding it is right there. So I want to know how fast is it going then. But remember, we said that this whole section, this whole area here, this from 2 until 3.5 seconds, it was going the same velocity. So it doesn't matter where along this line I find the velocity, it's all the same. And how do I find the velocity on a displacement time graph? I find the slope, which means I need 2 points. And I'm actually not going to use this point because I'd have to estimate a lot, right? I don't know where exactly that point is. It's a bit of an estimation as to what displacement that might be. However, if I use this point here at the top of the thing, right here, then I can use this point. Well, I don't know why we're not circling. And I can use this point. So I can use that, and I can use that as my 2 points. It works really well. So those are the 2 I'm going to use because those 2 will give me the slope of the line, and that slope goes right through the point I am worried about. So remember, my slope is my rise divided by my run. So I need my 2 points. And I want to pick points like I did that are really easy to read. So I have 9 and 2.5 as my rise. And then my run, I have 5 and 0. So when I do the math on that, I get 4.0, and it will be meters per second squared. No, not squared. Just meters per second, sorry. I had a moment. Meters per second. And that's because I'm taking the meters, the displacement, the rise, and dividing by the run, the time, and I get meters over seconds, or meters per second, my velocity. The second question asks me to find the average velocity for the first 5 seconds, which means I want to know what is the velocity when I consider going from this point to this point up here. Oh, I lost it. So there it is right there. Now, when I think about that, a lot happens, right? For the first 2 seconds, it's going one speed, and then the next 1.5 seconds, it's going a different speed, and then it's stopped for that. Now, I could find this speed, and then 0 velocity, and then I would have to find a ratio, like how long was it going this velocity versus being stopped. And that sounds like a lot of painful work to me. The lovely thing about graphs is there's another way. There's another way I can do this, because the other way I can do this is I can use graphing techniques. And by using graphing techniques, what that means is I can take a line and join this point to this point, and it automatically does all of that ratio averaging stuff for me. And it does it because I can just then find the slope of this line I just drew, because the slope of this line I just drew is going to be will give me my velocity, my average velocity though. And you'll see pretty easy points to deal with. I've got a point at 9 and 5, and then I'm going to use 0, 0. So how easy is that math, right? Nice, easy, simple math. So I'm just going to find the slope of that line I just drew. And the slope of that line I just drew, well, I said that my rise is 9 and 0, and my run was 5 and 0. So I do that math, and I find my average velocity, it does not look like a 4, there we go, make it 4 like, is 4, and again, meters per second, because I took meters and divided by seconds and found my slope. That's my average velocity. Pretty straightforward. Do you think I can do the same thing from this? It's saying the average velocity from 1 to 7 seconds. I should be able to do the same thing, right? All I have to do is join my point at 1, which is a bit of an estimate, to my point at 7 seconds, and find the slope of that line. So let's try it. You should be doing all this on your sheet yourself, right? You need to pause the video partway through, right, to catch up. That's cool. So I'm going to join those 2 lines. Use a ruler and join the 2 lines. Now the trick to this is to find a couple of points. So I'm going to go looking for points in the line. This is obviously a really good point. My original point isn't though. Look, I'm going to estimate a lot there, and I don't want to guess. I want something that goes right through the crosshairs. I want something that's really easy to solve, right? So that's what I'm going to go looking for. So I think that is right through the crosshairs to me. That's what it looks like anyways. So I would end up with these 2 points. So my rise is going to be 6 and 4, and my run is going to be 7 and 4.5. Now, maybe when you put 2 points on your line, you don't see those 2 points. Maybe you use 2 other points. Use 2 points on your line. When I mark this kind of stuff on a test, remember what I'm looking for is understanding. I'm looking for you being able to put the line on, find 2 points, and find the slope, right? Nothing too hard. I'm going to look at your actual graph. I'm going to look at your actual line that you drew, and that is going to tell me what your numbers are, right? So don't get caught up if you go and do this and you find that you get a different number. You know, I got 0.8 meters per second. Maybe you got 0.9. Maybe you got 0.7. That's fine because you used 2 different numbers. That's acceptable. The trick to this is to use the line, put the line on your graph, just like I drew my line, and then use 2 points on that line to find the slope. That's what I want you to do. Okay, our last thing it asks us to do is to sketch the VT graph that goes with it. But remember, we've already figured out what happens. It moves away at a constant velocity. Moves away at a faster constant velocity. It stops, and then it moves towards at a constant velocity. So that's what we're going to sketch. Now, sketching graphs is kind of an unusual thing, right? This is not something you've done before. It's not something you're really used to. So be patient with yourself. This is one of the harder things we do this year because it's a concept you probably haven't dealt with a lot. But the first thing I'm going to do is an axis, and then I'm going to put a V and a T. Now remember, when we deal with velocity, anytime we're moving away, we are above the line. Anytime we're moving towards, we are below the line. And that's because positive velocities are away and negative velocities are towards, because velocity is a vector. That's all it is. It's a vector value. And because it's a vector value, that means that it has a direction and a number. The direction away towards, the number, the actual physical value. So the first part, it said it was moving at a constant velocity away. So a constant velocity, a constant number above the line. Then it's a faster constant velocity. Now they have to join each other. So I'm just going to join each other with a line. But there we go, a constant velocity, but faster, right? There we go. And remember, this is a sketch. I'm not getting too excited. I'm not going to, get crazy about exact numbers, or I just want the shape, right? We're talking about shape. That's why it says sketch. It's basically creating the shape. Then it stops. Well, when it stops, its velocity is 0. Make sure that's very apparent. And then it has to have a negative velocity because it moves towards at the end. The negative is weird, I know, but you'll get used to it. That's the vector part of the velocity. So take some time. You'll get used to it, but think of those two parts, the number and the direction.